Now we want to look at the wave that is created on a string. We're going to look at the mechanics of that. We're going to look at the force and second law of Newton and see how a stretched string can support travel of a wave with a constant speed. Okay, so the first thing we want to look at is we want to look at, let's say, a small part of the string, and we want to look technically to come up with a free body diagram for that. Okay, so I'm gonna write the title wave in a stretched string. Okay, so if we look at a wave and let's say this is a tiny part of the string, I'm exaggerating the distance and angle for obvious reasons because I want to look at the forces. But if we look at this, let's say this segment starts at position Z and it ends at position Z plus delta Z. Okay, there's a tension on this side of the string, let's say T, okay, which creates an angle theta here, and there's a tension on the other side of the string. Again, T, the tension is the same. The tension does not change over the length of the string, and it makes another angle theta. Okay, so this theta at Z is the slope. Theta at Z plus delta Z is also the slope. The slope changes, so I'm gonna call the other one the theta prime. Okay, and here we have F. The y-axis is F, and this is the z-axis. Okay, now if we look at this, we can write the equation for the forces that are acting on this small part of the string. If we look at the forces, there's one force pulling it up, the other force is pulling it down. So the net force, okay, I can write the net force and say that is delta F in y direction, okay, in vertical direction is T sine theta prime minus T sine theta. Okay, so this is the force that it is experiencing. The wave that we are looking at are the waves that are not, let's say, very crazy. They are not too far away from the equilibrium length, equilibrium position of the string. Okay, so the distance and angles are exaggerated here. Usually, if the wave is not that big, the angles theta prime and theta are very small. Okay, so if the angles are small, what we can do is that we can switch between sine of theta and tangent of theta. Okay, you know, if you do first order or second order expansion, okay, if you expand these, you're gonna see the sine and tangent are very similar to each other if the theta is small. Okay, so we're gonna switch sine to tangent here because that helps us in the mathematics of analyzing this. Okay, so I'm gonna say the net force delta F is now equal to T times tangent of theta prime minus tangent of theta. Okay, and now what is tangent of theta prime and tangent of theta? That's technically a slope, which is the derivative of F with respect to Z. Okay, so that is, so this is almost equal, and that becomes again almost equal to T times derivative of F with respect to Z, Z plus delta Z minus the derivative of f with respect to z at z. Okay. And now if you look at this shape, this is derivative, the first order derivative at z plus delta z minus the first order derivative at z. They are subtracted. That can be written in terms of t times the second order derivative of f with respect to z times delta z. Okay, so this is the net force on these small segments of this string. Okay, so what do we know from the second law of Newton? We know that the net force, we are calling it here delta F, is mass times acceleration. What is mass here? We can assume that the linear mass density of this string is mu, so the mass becomes mu times delta z. Okay, for this piece of the string. What is A? Is acceleration in the vertical direction. Okay, so that's gonna be, if F is gonna tell us the acceleration, okay, then, sorry, if F is the position, then partial derivative of F with respect to t is gonna be the speed, and then the second derivative of f with respect to t is going to be the acceleration. Okay, so A is technically, I'm going to continue this to here, and this is going to be the acceleration that we have, which is d2f over dt2. Okay. So now, and delta F is just this one. So if we want to write the second law of Newton for this part of the string, we should write that delta F net force is the mass, which is mu times delta z times the second derivative of F with respect to t. And that becomes d2F over dt squared. Okay, so this is basically the second law of Newton. Sounds good? Okay, now we can look at this. Okay, and if we write this delta F in terms of the second derivative of force with respect to z, we can come up with the equation which is known as a wave equation. Okay, can I continue here? I think so. For one more step, I'm going to continue on this page because I want to have all of these on the same page. Okay, so delta F is t times second derivative times delta z. If I sub that back here, we get t times d2f dz2 times delta z is equal to mu times delta z d2f dt2. Okay, now delta z is cancelled out by this, and that's a good thing because the expectation was delta z is becoming very, very small, so we got rid of that. And we have t here, we got mu here, right? I can move t to the other side and write it in terms of, if we have a little more space here, I can write it in terms of, I'm going to go to the next page. Really can't squeeze everything here. So I can write that equation in terms of the second derivative of f with respect to z being equal to mu over tension times the second derivative of f with respect to t. Okay, this should be z squared as well. Okay, so now if you look at this differential equation of, again, f is being function of z and t, okay, it's a second order differential equation. One side is with respect to z, the other side with respect to t, okay. A common way of writing this equation is writing it in terms of, instead of mu over t, people write it in terms of 1 over v squared d2f dt2, and here d2f dz2. And the reason is that if you write it like this, with the definition of v being a square root of t over mu, we're gonna see in a minute that this v, okay, looks more like u, this v is actually the speed of the propagation of the wave, okay. Now this is the classic wave equation here, I would call it. This is the classic okay. So next I want to show you that any function of fzt which can be written in terms of g of z minus vt, as we discussed in the previous video, okay, any function that can be written in this form, which is a random wave propagating with constant speed of v, this function is going to satisfy the wave equation, okay. And here the interesting point is that I'm not making any specific assumption on what the g, the shape of the wave is. There is no assumption except that it's a function that you can take derivative of. It's a behave function, okay. And then I'm gonna do that in a minute by looking at these derivatives and see what happens next, okay. So to do that, we should first look at the derivatives of f with respect to z and t, and we should look at the second derivative. So we should take the first derivative, see how that simplifies, and then look at the second derivative, okay. It's a little bit of mathematics, but it's a little bit of easy mathematics, okay. So let's go step by step. Derivative of f with respect to z, okay. So we're gonna write it in terms of the function g, okay. So in order to do that, I'm gonna make the assumption that this z minus vt is actually u, okay. I'm gonna call that u, and I'm gonna use the chain rule to write this derivatives in form of g, okay, in terms of g. So df over dz, okay, I would write it in terms of dg over du, which is being derivative of this with respect to u, and then it should be multiplied by derivative of u with respect to z, okay. And now derivative of u with respect to z is just 1, so this is equal to dg over du, okay. And remember, f itself is again function of two variables, so we should write the in terms of partial derivatives, but g is function of a single variable, even though we are using z minus vt here, but that's technically just u, okay. As a function, it has just one single input, not two inputs. F has two inputs, okay. So dg over u is just simply the derivative of g with respect to u, okay, and this is, you can write d. For f, you should write partial, whether it's being with respect to z or with respect to t, okay. Now the second one, let's look at the derivative of f with respect to t, and again we write it in terms of dg over du, this time the partial derivative of u with respect to time, okay. So now if you look at this, the partial derivative of u with respect to t is not 1 anymore. Here we have negative v times t. So this itself is negative v. Okay, so partial f over partial t is negative of v. Okay, I apologize, my v's and u's are very similar to each other all the time, so I try to be more clear here. It's going to be negative v dg over du. Okay, and again remember, this dg over u, this dg over u, they are actually the same. Okay, so now what if we take the second derivative? Okay, because that's what we need here. Okay, so now let's look at the second derivative of, first let's say d2f over dz square. Okay, so we are taking one more derivative after this. Okay, so I can write it in terms of d over dz of df dz. Okay, but then up here we find that df over dz is dg over du. Okay, so I write that in terms of d dz times dg du. Okay, and now we use exactly the same chain rule. We first take derivative with respect to u and then multiply that by partial u over partial z, and that becomes second derivative of g with respect to over du square times partial u over partial z. Okay, and this again, this, the whole thing is 1. Okay, this 1, and so that becomes equal to d2g over du square. Okay, and now we do repeat this for second derivative of f with respect to t, and that is again partial over partial t, partial f over partial t. Okay, and this thing we calculated up there, that is negative v times dg over du, so it's going to be negative v times d over dt of dg du. Okay, now I use the same chain rule. I have negative v here, and then second derivative of g with respect to u multiplied by partial u over partial t. Okay, so partial u over partial t again is negative v. Okay, so this thing becomes negative v, and that thing combined becomes v square times d2g over du square. This should be square as well. Okay, so this is d2f over dt square. Right, okay, now look at this. Second derivative of f with respect to t is v squared d2g over du2. So we got this one. And then here the second derivative with respect to z is this. Okay, so comparing this with the right hand side of this, it's obvious that we can write that second derivative of f with respect to t square. Here we have v squared, so if I multiply that by 1 over v squared, that should be equal to this, which is d2g over du2. d2g over du2. Okay, now this is the same wave function that we had up here, and that means any function that has a form of fzt, which can be written in the form of g of z minus vt, satisfies this equation. And in the previous video we discussed that such function is definitely a random shaped wave that is propagating in the z direction with a constant velocity of v. Okay, now one little small thing here is this. We use z minus vt. What if I have chosen another function h being z plus vt? What would have changed in the whole calculations here? Instead of v, negative v here, I would have had positive v. Here, this would have changed to positive v. And all the way down here, we would have had positive v times positive v. That would have been again very similar. v2 times d2g over d2. So if I had chosen this h being z plus vt, again I could have come up with the equation here, okay? Come up with the equation here that satisfies the waves equation. So this is not the only solution to this wave equation. We could have z plus vt as well. Okay, now if we think about this, what is the difference between the two? G of z minus vt is a wave that is traveling in the positive z direction with the velocity of v. Okay. Z plus vt is a wave that is traveling with the same speed but in negative z direction. Okay. And from physical point of view, that totally makes sense. If you have a string that you can move and create one wave in positive z, most likely if you go to the other side of the string, you can create very similar wave traveling opposite direction. Okay, so the general solution for the wave equation can be always written in terms of f of zt being one function g z minus vt, okay, plus another function which is z plus vt. And that takes into account that waves can go both in positive direction, okay, and travel also in negative direction in the same media, okay. So with this one, I'm gonna stop this video here, and next we're gonna look at the sinusoidal waves that are waves of a spatial shape, okay, and they are very useful, and they are used a lot more in electromagnetism, because when we talk about electromagnetic waves, the electric and magnetic fields actually have the shape of sine and cosine. Okay, so I'm going to stop here and start another video for that.